are going to be equal to each other. So that's what we call a removable discontinuity. We also have, surprise, non-removable discontinuities. These are ones that are not easy to fix. Some examples of non-removable discontinuities are jumps or vertical asymptotes. For non-removable discontinuities, the limit as x goes to that value will not exist. And some examples of it, so we talked about the jump. The jump could have like filled in circles or open circles. That would be considered a jump and non-removable. For vertical asymptotes, even if they're going in the same direction, non-removable. If they're going in opposite directions, non-removable. Or even if you have like one side's the asymptote, but the other side's like a jump, those are all considered non-removable. And then, the vertical asymptote non-removable discontinuity also has another name. Sometimes you refer to it as an infinite discontinuity, which kind of makes sense. If it's approaching an asymptote, it's approaching something forever, and pretty much will always be discontinuous. So we have holes for removable, and then we have non-removable jumps and vertical asymptotes where the limit does not exist. Questions so far? All right. Nope. So then we have like our definition for continuity, and I definitely put lots of exclamation marks here because this is one of our like big overreaching ideas that we have in calculus, and it's going to be the definition for continuous. So like visually, we know that means you're not picking up like your pencil when you trace it. That's not a very mathematical definition. The actual definition for continuity does have 3 parts to it. The first part is that the value must be defined. So that's going to be a case where there's like an actual point there. Like if the point's not there, then clearly it can't be continuous. The second thing that has to be true is the limit has to exist. So the limit has to exist at that value. And I'm using C here, just kind of a stand-in. C could, of course, be any number. I do want to remind us again, for a limit to exist, there's kind of like a little subscript to this one. And for a limit to exist, we know that when you come in from the left, that has to be equal to what you're doing as you come in from the right-hand side. And then 3 kind of combines your 1 and 2. For a limit to exist, for it to be continuous, the limit has to exist. And whatever that limit is, it has to be equal to the value. When you see this statement in this class, that statement means the function is continuous at C. To put this statement into words is basically saying that the limit is equal to the value at some x value of C. So visually, what does that mean? We know for the limit to exist, what comes in from the left has to match up with what comes in from the right, and that's equal to the value of that point. Well, if what's happening in the left and the right is equal to the value, then you would have some sort of function that is continuous. So to me, that definition kind of just makes sense. Of course, I also have a degree in math, been doing math a long time, so hopefully that definition does make sense to me. But I do hope that you can see that and kind of see, okay, that does make sense. If you come in from the left and come in from the right and there's a point there, then that does mean the function is continuous. So why is this important? In calculus, pretty much when we start doing these things called the derivative and the integral, they only work when our function is continuous. So we'll need to know like when there are instances of it not being continuous. And then we also need to know, is it going to be something that we can easily fix, meaning it's removable, or is it just something that we can't fix, like if it's a vertical asymptote or a jump. So what we're going to look at is I just have several problems. And I just want us to discuss the continuity of the function. This one right here is kind of like a before calculus type problem since we're just looking at the graph. And then we'll start looking into some of the actual algebra of the functions, and we'll see how many we get through today. I don't want to keep you the whole period. But I have discussed the continuity of the function. I do want to be clear, when we see this in calculus, discuss the continuity, y'all have taken plenty of AP exams before or taken plenty of college board exams like the SAT. You know that they can sometimes be very particular with like when the question says this is what they actually are asking for. And this is one of those cases. When you see discuss the continuity, that is telling you to do two things. That is first telling you to determine where the function is continuous. And then the second thing you want to do is to classify each point of discontinuity. So like if it's discontinuous at x equals 3, state that, and then kind of classify what that is. So this first one is very easy. We have a graph in front of us, so we can kind of say, hey, this graph is continuous on. And for me, the easiest way to talk about where it's continuous is to use interval notation and work from left to right. So I see an arrow here, so it's going to start at negative infinity. I'm tracing it with my pencil. The first time I have to pick up my pencil is at x equals -1. Still tracing the graph. The next time I have to pick up my pencil is at 2. So we skip over 2. And then the last time I end up picking my pencil up is at 3. So we can visually see that this graph is discontinuous in 3 places. Another way you can write that, again, interval notation to me is the easiest. You should be able to read interval notation. But another way to write that answer, some people like just stating something like it is continuous everywhere, or for all real numbers, except, and then just lists where it's not continuous at. So it's not continuous at -1, 2, or 3. So that's the first part. We've talked about where it's continuous. And then we want to talk about where it is discontinuous. And when we talk about where it's discontinuous, when you classify it, you really only need to classify it in 2 ways. You want to identify where it is non-removable at, if anywhere, and where it is removable at, if anywhere. That first point of discontinuity, when x was equal to -1, was that non-removable or removable?
Removable.
So at -1, we see a jump, so it's non-removable. And then the next time we see a discontinuity is at 2. That's an asymptote, so that would also be non-removable. Again, we call that an infinite discontinuity. And then removable would be an example at 3. X equals 3 would be removable because that is just a hole in the graph. Now this one was pretty straightforward because you just had the graph in front of you. You didn't have to worry about solving anything. All the other examples we're looking at today is going to be looking at the functions. So a lot of those prereq skills are going to come into play. Knowing how these different functions look, knowing when like vertical asymptotes show up, and things like that. So for the first kind of algebraic example, let's do this one. I did make it a little bit easier for us by going ahead and factoring this one.
Mr. Brown?
But I did want to start with this one. Yes.
Yeah, could you go back for just like 2 seconds?
Yeah, sorry. I'm just so excited. I guess I moved ahead.
Yeah. Okay, got it.
All right. So the first function I want to look at is this one. So again, discuss the continuity of the function. This is a rational function. Again, if it was not factored, you would want to be able to factor it yourself. And remember when I say discuss the continuity, you want to talk about where it's continuous. And then you want to also talk about where it's discontinuous at. And we know we have two types. We have a removable discontinuity, and it could also be a non-removable discontinuity. Well, in a rational expression, where do we figure out where kind of it's not going to be continuous at, the numerator or the denominator?
Denominator.
Denominator. And that's going to be pretty much big idea. Like if you want to find where a function is discontinuous, often you want to set the denominator equal to 0 because you can't divide by 0 in math. So we do have some knowledge of these types of functions. Looking at this function, I see we have two factors in the denominator. I have an x plus 3 and a 2x minus 1. So I do know that x equals -3 is a point of discontinuity, and x is equal to 1/2 is a point of discontinuity. 4 is just a coefficient, no x there. So if I want to say where this is continuous at, it is going to be continuous everywhere except for those two places in the denominator. So again, I like interval notation. If I can do an infinity sign appropriately. But there's other ways you can write too, as long as you're clear about where it's discontinuous at. Or you can also say continuous everywhere. But x cannot be equal to -3 and 1/2. Both those ways of writing it are fine. And then this is where kind of your prerequisite knowledge comes into play. At -3, do I know that's going to be removable or non-removable, and how do I know?
Removable. Because it's a
It's
whole.
removable, and how do you know that x equals -3 is removable?
Because it'll cancel out from the like numerator and denominator, creating a whole.
Correct. So you know when it cancels, and this is why those prereqs are important. Since it cancels, you know on the graph that it is a whole, and we know that wholes are classified as removable. So building off of that, this other one, x equals 1/2, that does not cancel out. You know when things are left over in the denominator and don't cancel, then they are vertical asymptotes, which now we know we can also call an infinite discontinuity, which is a type of non-removable discontinuity. Questions on that one?
So if it doesn't cancel out to create a whole, it's automatically non-removable.
Correct, because it will always be a vertical asymptote.
Okay.
So like if this one did not have this x plus 3 in the numerator, like if it was just gone, then they would both be non-removable.
Yeah, I got a question.
Yeah, Mitchell.
What would a jump look like then?
Rational functions won't have a jump, but I'm glad you asked because I'll have one come up. As in, here's one that would have a jump. So piecewise functions. I tried to find like one that looks, I made up, but one that looks a little scary, like it has 4 pieces in it. But I want to use it to kind of talk about the discontinuities of it. So let's just talk about piecewise functions. So when you're looking at a piecewise function, we know that only certain parts of the graph exist in certain pieces, hence piecewise. When I think about it, I kind of think about like a number line. And I look for all of like the breaks in the graph. So like I see -2 is a break in the graph. I see 1 is a potential break in the graph. And I see 4 is also a potential break in the graph. And basically my thinking is sometimes when you have a piecewise function, you will have like one piece coming along, it stops, and the other one picks up somewhere else. While other times you might have a piece of the graph where one piece comes along, stops, but then another piece comes, fills it in, and then continues. So when we're talking about the continuity of a piecewise function, you basically need to check all of those boundary points by looking at those intervals on the pieces. So like the issues I have on here, there's a break in the graph at -2, there's a break at 1, and then there's a break at 4. And I'm going to space those out a little bit better. And we know basically is using limits, we don't have to think about it in terms of limits if it's easier for us. But basically want to make sure that the left-hand side and the right-hand side are going to like match up, and that will make it continuous. Or maybe they don't match up and they are not continuous. For example, this 2x plus 8 is going to exist if x is less than or equal to -2. So anytime I'm to the left of -2, this 2x plus 8 is going to be used. On the other hand, when I am between -2 not including it and 1 not including it, I'm going to be using the function 2 minus x. When I am between 1 not including 1 all the way up to 4 but including 4, I will be using the square root of x. And then if I am bigger than 4, then I am using this last function of 3 over x minus 4. So I want to basically find the value on the left and right hand side of each of these graphs. So when I'm looking at the values, we basically want to plug it in. So here's my work for it. Let me grab a different color. On the left hand side of -2, I'm using 2x plus 8. So I have like 2 times -2 plus 8. That's -4 plus 8 or 4. So that's going to be the y value on the immediately left-hand side of -2. On the right-hand side of -2, I have 2 minus the -2, and it gives me a 4. Those two numbers are the same, so I have two options here. We know they're meeting up together, like this example over here. They're meeting up together. And we need to figure out, do they meet and is it continuous, or do they meet and there's a hole in the middle? What option do we have at -2? Or I'll ask it this way. Let me ask it a little bit simpler. Is this function going to end up being continuous at -2?
Why do you say yes? Because it's also equal to -2?
Yes, so we're thinking about that three-pronged definition. It is equal to a value at -2, and the left-hand side and the right-hand side are equal at -2. So it's continuous there, so we can try the next one. So let's go ahead and see what happens at 1. On the left-hand side of 1, so I have 2 minus, plug in 1, and I get 1. On the right-hand side of 1, I have the square root of 1, which is also 1. So the left-hand side is equal to the right-hand side, but looking at my inequality, the x was never equal to 1, so I end up having a hole here. So to ask the question again, would this graph be continuous when x is equal to 1?
No.
No, and if we want to classify it as discontinuous at x equals 1, what type of discontinuity do we have?
Removable.
Removable or non-removable?
Movable.
Removable, because it would just be a hole in the graph.
How can we know that that's a hole and not an asymptote?
We know it's a hole because, I know you can't see me pointing, but the limit from the left and the limit from the right are both 1, so they're approaching a value.
Okay.
And so then we can try what's happening at 4, right? So then at 4, coming in from the left, it's the square root of 4. Coming in from the right, I have 3 over 4 minus 4. Well, the square root of 4 is 2, and from the right, we have 3 over 0, which we know is like undefined. So Armani, I think this will answer your question. This 3 over 0, what's actually happening on the graph at 4 for the very last function?
Is it a vertical asymptote?
It's a vertical asymptote. So this one would also be discontinuous at x is equal to 4, but it would be a non-removable one because we do have an asymptote at this location.
So that one's an asymptote because it's undefined. But if it was like two different numbers, it would be the
If it
red
was two different
graph
numbers,
here.
so I already made a piecewise function that had 4 pieces, which I think is a lot. I could have made it longer for more examples, and I have one later. But if you get 2 different numbers, then you would have a jump. So basically, if you get the same number, it's continuous or a whole. You have to see if it exists there. If you get something undefined, then you know it's an asymptote. If you get 2 different numbers, then you know that you have a jump. Does that make sense?
Yeah, that helps.
All right, so I'm gonna do one more and then stop for today. Actually, I'm kidding. Wait, do y'all wanna do one more or do you wanna stop for the day?
Stop.
Sure, fine with me. So I have 1, 2, 3 examples to do tomorrow. We will do a trig one tomorrow if you need to review how to solve trig equations and where they have asymptotes. But I will stop here today, so you have time to work on some stuff. So what I'm assigning, you have homework 4, which was already assigned. Now I'm assigning the last homework you have for this unit, and it's homework number 5. I am adding something because I think it's a little long. Odds only are only going to be required. If you want to do all of them, you can. Be my guest, do the extra practice, but I'm only going to require you to do the odds. We talked about the briefcase binder. You'll have time to work on that next week, but just know that it is a thing if you find yourself just wanting to get ahead. The other thing I am going to say, if you have any time during office hours, please log in and do a little bit of work on iReady. I really appreciate those of you who have already finished that. If you didn't get started, then you definitely need to log into iReady sometime before 4 o'clock today to get started on it. But that's basically the homework I'm going to be leaving with you today. I want you to finish up homework 4, ask me questions on homework 4. You can start homework 5, and then also the county mandated iReady assessment. Any questions on anything? Mitchell, you have your hand up.
Yeah, could you go back to that last slide?
Mm-hmm.
Is it
Before I do, anyone else have any questions on the assignments? All right, so if you're good to go, you can go ahead and sign out of the meeting. Mitchell, there you go for that problem. Again, please make sure you continue work on your homework and work in iReady. Remember, your first test is going to be next Friday, not next Wednesday. I pushed it back 2 days. So we'll finish up notes tomorrow, and then basically all next week is going to be review. So we'll have plenty of time to review and make sure that we are comfortable and ready for our first test. But if you're signing out, have a good afternoon, and I will see you tomorrow.
Bye, Mr.
Rachel, you have
Brown.
your hand up. What's up? Bye, Marnie.
Can you go over question 4 on day 4 homework or unit, whatever the number 4 on that homework?
Question 4 on homework 4. Is that what you said?
Yeah.
Yeah. So for that one, this is the limit as x goes to infinity. So if you're working on that one, you have the limit as x goes to infinity of this function. And so for these intuitive ones, we're going to think about, like, I know we can't really plug in infinity, but in our heads we're thinking about, like, so I have the cosine of pi e to the negative, and x is going to like a really big number. When you're dealing with limits, negative numbers can be kind of hard to deal with. So what can you do to make that have a positive denominator? Let me say that again. What can you do to have a positive exponent?
Make it a fraction.
Make it a fraction, so you can rewrite it as the cosine pi over e to the infinity, so it's now positive. And that's a little bit easy to work out because if I have pi over a really big number, what is that going to go towards?
Infinity, so it doesn't exist.
Try again. if you have a number over something really big,
It goes over 0.
it goes to 0. So this actually becomes the cosine of 0,
Oh, okay.
which is, of course, 1.
Thank you.
So it's actually very similar, like you get almost a very similar answer to number 5, where it's a real number. It's just kind of dealing with an infinity instead. And then you have 6 start as well, I see.
Yeah, I think I can do 6 by myself since we went over 4 because it's a similar
Yeah.
idea.
It has a similar kind of process, but it is a very different answer, I will say. But I'll let you kind of think about it yourself first.
Okay.
I have a question on like 14 on question on the 4 homework.
14, you said?
Yeah, like the 14 through like 19.
Is that the
Probably-
piecewise one?
Yeah, like
So I think maybe that one problem we did today might help you with it. But like if you're looking at that one, you still have to just make sure you choose the right like piece of the graph.
okay, yeah.
And so like this first one, if we're going as x goes to infinity, like if I just kind of highlight if x is going towards negative infinity, then that's going to be this function. Where x is less than -3.
Yeah, okay. That's I just
Some of them they have to be careful with, like -3 from the left, you need to make sure, okay, if I'm coming in from the left-hand side of -3, then it's still going to be that first graph.
okay.
But then if I do, let me find one, like if I had you do what's the limit as x goes to 0, which function would you have to use?
You'd have to
Just
use
0 overall.
right.
You use actually the second one and the first one and the third one.
Oh,
Because remember, for a limit to exist, you have to know that the left-hand side is equal to the right-hand side. And since that is a boundary point, you would need to check for both of them.
okay.
And then if they're equal, then of course that's your answer. If they're not equal, then you have D and E. But then if I had like, it's not a question on here, if I said find the limit as x goes to -1, then you would just have to worry about doing one function because -1 is between the intervals.
Okay. All right. Thank you.
So yeah, just think about like which piece you have to use to kind of answer the graphs. And if you're going from both directions, just make sure that you're not on a boundary point.
Okay. Thank you.
You're welcome.
See you tomorrow.
See ya.
Yeah, so I actually could use help on that number 16.
So you end up with cosine of like pi times infinity.
Pi times e to the infinity, yeah.
Yeah, so basically you have like the cosine of a really, really big number.
Yeah.
Well, what does cosine keep doing as you go out to a really, really big number?
Oh, I forgot what the correct term was. It keeps
It
going
goes up and down, right? Oscillating, I think is the word
Oscillating,
you're
yeah.
looking for. So if it's doing that, then
It's
basically the answer is D and E.
Okay.
Because you can't pick a value because it's just always like as soon as it goes up, it's going to start going back down again.
Okay. That
So
makes
it's D and E.
Okay.
Anything else?
Nope, I'm good. Thank you.
All right. See you tomorrow.
See you tomorrow.